This is a pleasure for me to introduce our friend Barbara Nelli from Università dell'Aquila. She's going to talk about hypersurfaces with constant higher order mean curvature. Thank you very much, Barbara, for your participation here.
Thank you, Asun. First of all, I would like to thank the organizers for inviting me. And it's always a pleasure to be in Brazil. Of course, it's different this time, and to find you, all of you here, give me a lot of saudade. But I will try to stay to keep my capacity of giving a talk anyway.
We miss you a lot, Barbara.
Thank you. So let's go. I will talk about hypersurfaces with constant higher order mean curvature. So first of all, let me just specify a little bit better the object we will deal with. So we take an immersion of a Riemannian manifold of a dimension n in a Riemannian manifold of a dimension n+1, so an hypersurface. And we will consider the R mean curvature of the immersion that is defined as the elementary symmetric function of order R of the principal curvature, K1, Kn of the immersion. This is a standard definition. And it's clear then when we consider H1, this is the mean curvature, while Hn is the Gauss-Kronecker curvature of the immersion. And usually, in all the talk, our ambient manifold N will be the Euclidean space or the hyperbolic space, and sometimes at the end the product space Hn, so the hyperbolic space cross R. Of course, the first two are space forms, and the third one is not a space form, so this gives some different and interesting results. Okay, it's clear that the HR, besides being defined as a very natural function of the principal curvatures, so they carry a lot of geometry, they also come from another interesting notion that was introduced by Robert Riley in 1973, who studied a set of variational problems defined as follows. So you take an immersion of a hypersurface in Rn+1, and you define the usual variation of the immersion, like a set of differentiable maps, like a differentiable map from 0, 1 times m into Rn+1, such that at each stage fixing T, X, Tp is an immersion. And also for T equals 0, you have X, and this fixes the boundary. The immersion, and all the immersions have the same boundary. Then you can define a volume for this variation, defined as it is here. And in fact, it's a volume. It's an algebraic volume. I will not enter in details of it. And then you can define this AR of T as the n over R of HR, where HR is the R-symmetric function of the principal curvature. It's clear then when HR is, when you integrate one, you have the area. That is the standard fact when you have mean curvature, but you will see it in a moment. Then you can compute the derivative of V and the derivative of AR with respect to T, and you get these nice formulas. It's very, very easy formula where N is the unit normal vector field to M. This is N. So what happens? if you denote by JR the area, the R area, let's call it R area, AR, plus lambda times the volume, where lambda is a constant, and you take J prime over, you do the sum, and you see immediately that if M as constant HR plus 1, then you can choose lambda like this constant, HR plus 1 times N over R plus 1, and it's clear that M is a critical point for JR because this is equal to 0. Okay, so this means that hypersurfaces which has an hypersurface that has a constant HR plus 1 is a critical point for this functional. That is exactly the same. It's analogous to the situation for the mean curvature when you take the area instead of AR. Okay, so it's really very natural to consider them, also to consider the R mean curvature also from this point of view. Okay, but now let me enter a little bit more in details about HR and talk about ellipticity. If you take the equation of HR equal to a constant, this yields a second order fully nonlinear partial differential equation. And this is elliptic provided the vector of the principal curvature belongs to the component of Rn plus 1 of the set where HR is positive and contains this point. This is a cone, in fact. And in this case, you can say that an hypersurface which HR constant satisfied an elliptic equation. I'm not very precise about which is this elliptic equation, but for example, you can consider just locally the surface as a graph above the tangent plane, and this give you an elliptic equation for the function described in the graph. But you can see it in many different ways. Anyway, it's elliptic. So in general, if you take HR equals 0, this does not yield an elliptic equation, except when you consider the mean curvature, that is always elliptic. But sometimes, yes, and we will see in a moment when this will happen. Okay, so why ellipticity is important? Because it yields the maximum principle. Okay, so you know that many of the results and the properties of constant mean curvature surfaces or minimal surfaces are given by a very strong tool is the maximum principle. So you can have many properties here when the maximum principle yields. Okay, so let me state the maximum principle here. So denote by N an orientation for the hypersurface, and K the principal curvature vector, kappa the principal curvature vector of M. Then we have this maximum principle that is very, it's the same as usual. I mean, if you have two hypersurfaces in a Riemannian manifold with the same HR, positive, and you have a point P where they coincide, and even the tangent plane coincides, and you are considering the same normal vector, and you compute the principal curvature of M with respect to this normal vector, and they both, this vector, this kappa, both belong to this positive cone that I defined before. Then, if M remains on one side of M prime around P, they must coincide. Okay, so this is the standard maximum principle. Let me, this was proved by Fontanelli Silva in 2001. Let me say that a lot of time I will cite Brazilian mathematicians. So this is really a tribute to Brazil also in this sense. Okay, let me also say what happens for HR equal to 0, so that we will state the maximum principle that we will need all over the talk. In this case, there was also the intervention of Oni and Leite. And you have the same, but provided that the rank of the Gauss map of one of the two surfaces is larger or equal than R. Okay, and then you can really prove the same maximum principle. I don't repeat it again. This fact that the rank of the Gauss map is larger or equal than R coincide with the fact that there are at least R KIs that are different from 0. And the proof relies on the properties of hyperbolic polynomials, because HR are hyperbolic polynomials, and so you have a lot of properties. I will not prove it, of course. Okay, so let me recall some results about HR constants in here for the moment in space forms. I will be very quick about that, but it's interesting because in the 80s there was a lot of work about the compact case. I mean, hypersurfaces of constant HR compact. For example, the Caffarelli, Nirenberg, Sprague, they studied existence and uniqueness of solution for the Dirichlet problem for HR equal to a constant. So, given a domain, I mean, now I put the boundary in the plane, but it's not necessarily in the plane. It's something like that. And they, it was very interesting because, as Pablo recalled yesterday, for a fully nonlinear equation, partial differential equation, Schauder theory in general does not work. So you have to find C2 a priori estimates for solving the Dirichlet problem. Because for quasi-linear, Schauder theory tells you that C1 estimates are enough. Then there is Latizanskaya, Uralchayeva theory to give you C1 beta, and then Schauder theory to give you C2 alpha. But here, when you have a fully nonlinear, you need to find C2 a priori estimates for solution. And this was very hard, and this was the hard job of Caffarelli and Nirenberg Sprague there. That opened really a new set of problem giving this answer. And then the other very interesting fact that was proved at that time was the classification of compact hypersurfaces with constant HR without boundary. And this was done by Ross and also by Corvar, because Ross, I mean, there are many papers, but anyway, I will tell you something more in a moment. But the fact is that the round sphere is the only compact hypersurface with HR equal to a constant embedded in Rn+1. Okay, so of course, the case R equal to 1 is Alexander's theorem, and of course, there are counterexamples. If you are immersed, everyone knows when to try, but there are also the spheres by Xiang, Teng, Yu. And then, yes, I want to tell you something about the proof here. I mean, the proof was in Journal of Differential Geometry by Antonio Ross. Then there is an appendix by Corvar that prove it for HR equal to a constant. But in the same years, more or less, there was another paper by Ross and Montiel that did it in space forms, but everyone used different techniques. I mean, the technique that Corvar used was maximum principle, but Ross and Montiel used some Minkowski formula and Rayleigh formula, so it's quite different. This is just a little bit of history about that. Then there were a lot of, plenty of results about compact hypersurfaces in space forms with a boundary and the classification about that. So you put a boundary and you look for symmetries again, no? Because this theorem by Ross and Carevar, you can think about it just looking for symmetries, no? So that it's a round sphere, so are all the symmetries. And here, when you put a boundary, you can look for symmetries, for example, inherited by the boundary. And there are a lot of results in this sense. Okay, but let me go to with what will be really the subject of this talk. I know that I am talking already since 15 minutes, but it's a little bit late to say the subject, but that's it. So we will mostly address three kinds of problems here. The first one is, we will not be compact, in fact. So the first one is about Bernstein and Schoentype's theorem. So we will study the geometry of a complete hypersurface with constant HR with respect to geometry of the asymptotic boundary. Then we will talk a little bit about rigidity, that is, if it is possible to perturb the arming curvature of a hyperplane, of a horosphere, or of an equidistant sphere in the hyperbolic space, keeping it constant outside the compact set. So you take a horosphere and you perturb it in some way in a compact, and you see that if it is, in fact, it is possible to perturb, or you stay with the horosphere. And then, oops, the last part, but I'm not sure I will have time for that, we'll talk a little bit of stability for HR surfaces. Okay. So let me start with the first result. As I told you, we will see properties of the hypersurface depending on the boundary. So the theorem is the following: is a joint work with Jin-Yong Zhu. Let M be a complete hypersurface properly embedded in the hyperbolic space with constant positive HR, and consider that the asymptotic boundary of M. So in the case that the asymptotic boundary is a point, then M is a horosphere. In the case the asymptotic boundary is a sphere of the right dimension, of course, and M separate poles of the asymptotic boundary. You know that you can see the asymptotic boundary of the hyperbolic space as a sphere, so separates poles. Does make sense. In this case, M is an equidistant sphere or a hyperplane. Okay, so this is this is the same slide. So this is a generalization of a result by De Carmo and Lawson in the 80s, and that was for constant mean curvature hypersurfaces of the hyperbolic space. Okay, so let me give you an idea of the proof. Okay, so the first thing to do is that, in fact, for these hypersurfaces, you can use the maximum principle. And all you have to do to prove it is that you are in this positive cone with your principal curvature. So, for example, it is enough to prove that you have a strictly convex point on the surface. So let us prove that there exists a strictly convex point on M. In order to prove it, I will do some picture. So you consider the, you consider the half space model for Hn+1. So this is the boundary at infinity. And and you have your surface M here. As the boundary at infinity of M is a point, we can choose the point at infinity that is not here in this part of the boundary at infinity. But it's the same boundary at infinity as the orosphere parallel to the asymptotic boundary. Okay. Now it's very easy because you can consider. Let me remove this because it's not very useful. You can consider, for example, you fix a K0 positive, smaller than 1, but it doesn't matter. And you consider the equidistant spheres whose principal curvatures are K0, okay? And of course, you can take it, you know that these equidistant spheres are like that, with a certain angle depending on K0. And then you can increase in order to get the first contact point here. I'm not very firm with my hand. It's not very good. Okay, so you have here the first contact point, and here you can consider you consider the tangent plane, hyperplane here, and you fix a direction x, and you also fix the vertical direction en plus 1, and you consider two planes P, that is the span of x and en plus 1. Okay, and then you consider gamma x equal to m intersection, let me call it px. This is a curve, and it's clear because m is above this equidistant that the curvature of gamma x is larger than K0. So the normal curvature. Km of gamma, no, sorry, Km of gamma x is larger than K0, larger or equal, let's say. So this means that this point P is strictly convex. Okay, so you have a strictly convex point. Then you can apply the maximum principle. And being able to apply the maximum principle, you can do Alexandrov reflection method with hyperbolic hyperplanes and prove that, in fact, the hypersurface is a orosphere. Let me sketch briefly the proof of this. So again, half space model. This is the boundary at infinity. This is the hypersurface M, and that this time you, as you have to do Alexandrov reflection method, you need hyperplanes. So you start with the hyperplanes here. Okay, you take one, and then you take first tangent one, and then you do it a little bit larger, and you start to do reflection. So this is the usual way of doing it. You denote by omega minus one of the two connected components, omega plus the connected component that contains at infinity the same point at infinity of M, and then you call the lower part of M, the part, let's say here, of M, if this is HT, this plane, this green plane is HT, is a family of plane. Let me put the right color, HT. So, the part below HT is MT minus, the part above on the other side, so here is MT plus, and the reflected part is MT star. It's clear that at the beginning, M star T is contained in omega plus, but we state that I mean, this holds all the time, because if this condition, if there is a T where this stops, stops to hold, then there is a first one when it happens, let's say T tau, let's say tau. And in this tau, it's clear that what happens is that the maximum principle give you a contradiction, because this would be M star tau equal to M plus tau by the maximum principle, and this is a contradiction because M is not compact. Contradiction. Okay, so this holds all the time, but this is very easy at this point to see. If this holds all the times, you get very easily that the tangent plane, where can I write it here? This implies that the tangent plane, Abel plane, but anyway, the tangent plane to M is always horizontal. Because if it was not horizontal, it would be very, very easy to find an hyperplane for a specific T such that the reflection would not be in omega plus. Okay, so when the tangent plane, as the tangent plane is always horizontal, this gives that M is Eurosphere. Okay, now, so we are done. Of course, the case where the boundary is spherical, this second case here is a little bit more involved, because even in order to find the strictly convex point is a little bit more involved. You don't have all the freedom that you have in the other case, but you can do it, and this work. I have to say that the proof is really the direct generalization of the Carmel-Ozone. It's just an adaptation to this case. Okay, good. So this is the first result, and then let me just mention the second result in collaboration with Jing-Yang. This is the rigidity stuff that I was talking about before. If I have a hypersurface which coincide with the Eurosphere outside the compact set, and if I assume that HR is larger or equal than 1, or HR is smaller or equal than -1 in module, then sigma is Eurosphere. Okay, so you cannot perturb an Eurosphere inside the compact set like that. Here you are still in H and +1. You can perturb it provided you keep HR on, let's say, larger or equal than the curvature of the Eurosphere. This is a result that was inspired by a paper by Rabaswam that did it for constant mean curvature surfaces, and for the mean curvature, I mean. And he was inspired by Gromov. Of course, Gromov did state this theorem only for planes in Rn. That is the same, because this theorem holds for equidistant, for plane, for everything. Yeah, but Gromov stated just for planes in Rn and gave a completely different proof, if any, I mean, a proof. And Rabat did it with the maximum principle, and it's the same for HR surface, hypersurfaces. Okay, so now let me go to study HR hypersurfaces in the product space. So here the situation is different for many reasons, principally because well, the ambient space, as you know, has no constant sectional curvature, so many things change. We will revisit two classical results that hold for minimal surfaces with finite number of ends in R3. Well, this is just a little picture for those, but here there is no one, I suppose, in this condition that do not have a precise idea of what HN cross R is. It's just HN, and we will take, usually we will take the hyperbolic metric, the disk model, sorry, the disk model for HR, so HN, so this is the hyperbolic metric here. And then you have the vertical component, that is dt square. Okay, so let me, before going in HN cross R, stay a little bit in H2 cross R, where you can see picture easily. And here are, I told you that I want to study hypersurfaces with respect to their asymptotic boundary. Okay, so for example, there are these two very nice examples: the vertical catenoid in H2 cross R, whose asymptotic boundary is just two circles, and then what is called the horizontal catenoid, that is a minimal surface again, and it is asymptotic to two vertical planes, totally geodesic planes. Okay, those pictures are by Paco Martin, Rif Mazzeo, and Madalena Rodriguez. Are taken from one of their papers. Okay, so it's interesting to understand under which condition a surface is one of that, or is asymptotic to one of that. Is a classify is interesting in this setting. Okay, so in fact, with Maria Fernanda e Vaussi, so more Brazilian in my talk, we got this result. If M is a complete connected embedded hypersurface in HN cross R minimal, so with HR equal to 0, and with this assumption HR plus 1 different from 0 guarantee you that you can use the maximum principle. Then assume that, and it's very natural to assume in this setting. So if you assume that M has two ends, and each of them is a vertical graph with asymptotic boundary, a copy of of a circle, I mean, like that, just this. Okay. Then M is isometric by an ambient isometry to a rotational invariant hypersurface. Okay. So it's why I call it Schoen type theorem, because all of you know this very important theorem by Rick Schoen: a complete and connected minimal surface immersed in R3 with two embedded ends of finite total curvature is a catenoid. Okay, so of course here it's different, but the spirit is the same. And it's important to say that for Schoen, finite total curvature guarantees that the ends were well behaved at infinity. But here we cannot say finite total curvature in this direction, because as it is asymptotic to an H2 at infinity, it cannot have finite total curvature. So we give a regularity, a different kind of regularity at infinity. We state a different kind of regularity at infinity, and this one. Each vertical graph of the asymptotic boundary is a copy of the boundary at infinity of Hn. Okay, so I have to say that the minimal case was studied in another paper with Sarp and Tubiana. But of course, in our paper with Fernanda Evaussi, we have also to classify the rotational, our minimal rotational invariant hypersurfaces, and to find them and to classify them. Okay, so this is the first result, and now the second result is a different taste. It's more like Osserman theorem. So let me state Osserman theorem. If you have a minimal surface immersed in R3 with finite total curvature complete, then M is conformally equivalent to a compact Riemann surface with a finite number of points removed, the ends. Moreover, the Gauss map extends meromorphically to the punctures. Okay, so it's very classical theorem, very nice and interesting. There was an extension to higher dimension for minimal hypersurfaces by Anderson. Of course, the extension cannot be exactly the same, because instead of conformally equivalent, Anderson had diffeomorphic. Instead of meromorphically extend to the puncture, he has a smooth Gauss map. Okay. What we do is to study complete hypersurface in Hn cross R, provided they satisfy a finite total curvature assumption. So we are in a different situation with respect to before, where we knew from the beginning that the total curvature was not finite, no? Because it was asymptotic to an Hn. But here we are, so we changed the point of view. We are more considering the example that I showed you before, the catenoid with the asymptotic, was asymptotic to vertical planes. That one was with finite total curvature. But so first, we study in general complete hypersurfaces, regardless the curvature, I mean the HR curvature. And then we specialize to HR equal to 0, and we get some more results. Okay, so we have to give the notion of finite strong total curvature. But we state the theorem before, and then I will say what is finite total curvature. So the theorem that is with Fernanda is the following. Let X be an orientable complete hypersurface with finite strong total curvature. Then what we get is that the immersion is proper, and M is diffeomorphic to a compact manifold minus a finite number of points. So just the finite total curvature give you properties on the end of the hypersurfaces. Okay, so let me give the definition that is a little bit involved of finite total curvature. If you take the shape operator of M, we define the strong total curvature of M. This norm of the second fundamental form in this weighted Sobolev space. So we assume that the norm of the second fundamental form is in this weighted Sobolev space, is this one. I will not read it. Just I just say that the distance from a fixed point of the hypersurface is involved. So we say that it has finite strong total curvature if this quantity is finite. This is not, I mean, it seems very a little bit ugly, not very, but ugly. But in fact, the norm was used by Bartnik in his pioneer paper, and it needed to define a suitable decay to infinity of the metric of a manifold that guarantees that the ADM mass was a geometric invariant. Okay, so it's not, it's something, it's something old. And this notion of strong total curvature was first introduced by Carmo Albert, so Manfredo and Fernanda, for hypersurfaces in Rn+1, and we use it also in this case. Okay, so in the case of finite strong total curvature, we have this theorem. Moreover, now we add, let me add the assumption that HR is 0. So minimal, are minimal hypersurfaces. And the theorem is as follows. So is our, so I mean, in some, we get the, we obtain the shape of the ends. So we take an orientable, complete hypersurface with finite strong total curvature and HR equals 0. And then, as we have the previous theorem, we know which is the structure. So we have a compact stuff minus a finite number of points. So we take the neighborhood of one of these points, y, this is E, and we consider the a unit normal vector field on E. Moreover, we consider a hyperplane of Hn cross R such that the boundary is contained in one of the half spaces determined by P. Let me do a picture to understand it. So we have our Hn cross R, and then we have, I take hyperplane like that, a vertical hyperplane. Of course, it's a vertical. So this means that, for example, the boundary of E is here, and then this is the boundary of E. And then you have that E is, I mean, you have something on the boundary at infinity of your end. And you know that for this part is contained in the boundary at infinity of the hyperplane. Okay, so let me change the color. So here and here is contained the boundary of E. You don't know anything on the boundary here and here. You know something only on the boundary in the vertical part. But then what you get is that, in fact, E is asymptotically close to P everywhere. And for any sequence of points converging to a point in the boundary at infinity, the last component of N converges uniformly to 0. That means that the normal becomes horizontal. Okay, so you really have that those ends are well behaved, really well behaved. Okay, sorry. In fact, this result generalizes a result by Laurent Auswirth-Rosenberg and also by Auswirth, myself, Sarp, and Tubiana. But the proof takes inspiration in a completely different setting. No, I mean, it's always minimal surfaces, but for completely different reason. This proof was for something else. I will not, of course, enter in the details of proof, but I want just to say that when you work with n larger than 2, you lose completely the technical support of complex analysis that was fundamental in those results here. And of course, r larger than 1, you weaken a lot the technical support given by the theory of quasi-linear PDE. So it seems very, very natural, I mean, it seems reasonable to require a stronger assumption on the total curvature. No, because we have a stronger assumption. We just usually finite total curvature does not involve the derivative of h. We need to take also the derivative of the norm of a to get something, but it looks really natural. Okay, so now in these last 4 minutes, I want just to tell something about stability. And this is a work in progress. So okay. You remember the characterization by Riley with as HR surfaces as a critical point of a functional that was this functional here. So you it's classical stuff. You say that something is stable. So in this case, you call it R stable if it minimizes this functional. So the second derivative is larger or equal than 0. Okay, one can easily extend this notion of stability when the ambient manifold is a space form, because Riley just did it in Rn+1, but Barbosa-Colares did that also in any space forms. But when the ambient is a general Riemannian manifold, there is not known functional for which hypersurfaces with constant HR are solution of the associated variational problem. So there is no variational problem known, as far as we know. But then you can always compute the linearized operator of HR. And you compute it, and you get this kind of operator, where PR is the classical Newton transformation that you can define inductively like that, starting with the shape operator. And here Rn is the curvature tensor of n. Notice that in space forms, these terms disappear. And then your TR is an operator, sorry, in divergence form, and you have all the good properties that you need. I have to say that this part is with Maria Fernanda Albert. It's a work in progress. Okay. Then in this, I wrote it here. I forgot it. So in this paper with Fernanda, we gave a notion of stability that was inspired, in fact, by the thesis of Antonio Bueno, by this paper, so by Bueno, Galvez, Mira, using the stability operator, okay, that we got before. And we say that M is R stable if there exists a positive function such that TR of U is smaller or equal than 0. Okay. Another way of giving the notion of stability. Of course, TR is not self-adjoint in general, but in fact, we can define a symmetrized R stability operator such that if M is R stable, then you have this. Okay, so you can work also in this sense with the stability operator that is a nice one. 1 minute just to tell you some results and plan. More than the results, and I prefer to tell you about the plans. As usual, you can define a weakly stable. When you have stable, you can define the weakly stable by assuming these properties of test functions. And you can ask at least a couple of questions. First, are compact rotational HR hypersurfaces for H large enough here, for H large enough, weakly stable or not? And this, for example, this is a result in H2 cross R and S2 cross R for the case of constant mean curvature by robust one. They are weakly stable. And the big question that we would also like to address is this one: under which condition on the constant HR complete or stable hypersurfaces do not exist. Okay. For the case of constant mean curvature, we got it, and also Chang, we got this result. We gave the condition independently in me and Fernanda Rosenberg, and also Xu Chang. But here the question is very challenging in our opinion, and we are trying to do it. Okay, I'm sorry I got 1 minute more, but thank you very much. And I hope to see you soon here, really.
Thank you, Barbara. So there was a question on the chat from Professor De Tang.
I am going to see. Is it true?
I think it's about the Schoen theorem.
Wait a minute. Which one? Because is it true what? Maybe
about that was Fernanda.
Not this one. Yes, but what should be true?
You suppose the two ends.
Yes.
I want to know if it's true, if you assume more than one end.
Okay, I see. No, so I don't know, because if one has more than two ends, I don't know if we are able to wait a minute. Two ends that are vertical. No, I don't know if it's true. I don't know.
You really need two ends, right?
Yes. Yes.
Thank you.
Is there more questions, comments?
Yes, I have a question. Hi, Barbara.
Hi.
So about this stability notion that you mentioned at the very end, do you have examples? Like I guess, for instance, that graphs should be stable for this function?
Yes, graphs are stable, and let me put it here. Okay, graphs are stable, and for example, we think that we can prove that. I mean, we can prove it that there is no compact or stable hypersurface. So this is a negative example in some sense, but graphs are stable because you can prove that if you find the Jacobi function by taking the normal, a positive Jacobi function by taking the normal times the vertical. So the normal is this function is positive. Okay, and it is a Jacobi function for our operator. So the graphs are stable. We have not many examples. Okay, so. Okay.
And so is it possible that maybe by looking at the rotational examples with HR equals 0, with HR constant, sorry, that you can have some kind of idea like the critical mean curvature type for these?
Yes, I mean, I know your paper with Ronaldo about all the HR hypersurfaces. So also in SM, because we were I mean, studying, first of all, things in H and crossover. But in your paper, there is also the classification for SN crossover, in SN crossover, and we're looking at that. So it's possible that some of them, when they're not compact, then they can be stable.
Okay, I understand the answer, but I did not write any paper with Ronaldo about any of this.
No, it's not. Who is asking? Sorry.
Oh, Pablo Mira. Pablo.
Ah, Pablo. Sorry, Pablo. I did not understand that it was you.
Okay.
I thought it was another Pablo because I don't see anything. So,
Okay.
so because I see only my present. Sorry, Pablo. I was.
Okay,
but you understand the answer. Okay. I thought it was Pablo dos Santos, the one that did the talk yesterday.
It was João Paulo.
João Paulo. It's not João Paulo, Pablo.
You're forgiven.
But it's crazy because I did not recognize Pablo's voice, and I know Pablo, but I was convinced, you know, when you are convinced who is the one that is asking.
Thanks, Barbara.
You're welcome.
Is there more questions? So if not, let's thank Barbara again. Thank you, Barbara.